let's get started. So we are very happy to introduce Christian Gaetz from MIT, who will be talking to us today about separable elements and splitting of Weyl groups. Okay, take it away.
Thank you for the introduction and for the invitation to speak today. So in the pre-seminar, I just plan to give some background on root systems and Weyl groups, parabolic subgroups, parabolic quotients, and a few examples, so that hopefully everybody is up to speed when it comes to the main talk. So start with the definition of a root system. So a root system is just a collection, which I'll call phi, of vectors in a vector space satisfying a few conditions. So the conditions are that the vector should span the space. The most important one is this second bullet point. So phi should be closed under the reflection across H alpha for alpha in the root system. So here H alpha is the hyperplane perpendicular to the root alpha. So in this picture labeled A2 here, in this picture, I've drawn the roots in blue. So these are these vectors of the form EI minus EJ. And in red, I've done my best to draw hyperplanes perpendicular to these roots. So if you notice that given any one of these red lines, if I reflect across that line, my root system is symmetric. So it has symmetries across all of those lines. And if we were in higher dimensions, I would have hyperplanes instead of lines. Okay, so this example that I've been referring to here, this example is called A2, type A2, and it's living, really it's most naturally seen to be living inside of the space where the sum of the coordinates are 0 inside of three-dimensional space. So this is called, in general, we have a type AN-1 root system is the root system where I just take all differences of my basis vectors. So another example is type B, which is drawn here. So in this example, you see there are more roots. So this is B2, and now I have all roots of the form a sum or difference of standard basis vectors together with the standard basis vectors themselves. So now we see that the hyperplanes in this picture actually are parallel to some other roots, but we still have symmetry about all those red lines. Okay, so that is the definition of a root system. What we're going to be interested in through most of the talk is an object associated with the root system called the Weyl group. So we know that this root system has symmetries about all of these red lines, these reflections across the hyperplanes H alpha. And the Weyl group is just the group generated by these symmetries. So it's the group, we could think of it as a subgroup of the orthogonal group of whatever vector space we're working in, generated by sigma alpha, which is what I'll use to write, is what I'll write for these reflections across the hyperplanes H alpha. So this is a generating set for the group we're interested in, but it's not a minimal generating set. So to get a minimal generating set that's gonna be relevant for the combinatorics we're interested in, we're going to choose what's called a collection of simple roots. So this will be some subset of my root system. So here I'm drawing the simple roots in green. So I'll use delta to denote the set of simple roots. So in this case, I have two simple roots, which are these, E1 minus E2, which I'll call alpha 1, and E2 minus E3, which I'll call alpha 2. So how I came up with this choice is that I chose a generic hyperplane. So some hyperplane which is not perpendicular or containing any of my roots. So that's this dashed gray line. This divides my roots into two halves. So phi plus, the positive roots, are those on one side of my dividing line, and the negative roots phi minus are on the other. The simple roots then, one can show that there is a unique basis of the space such that all positive roots are positive linear combinations of my simple roots. So in general, you should think of this, if I look at the cone, this cone here, generated by all of my positive roots, the sort of vertex rays of that cone will be the simple roots. So here I've got these two simple roots, alpha 1 and alpha 2, and the only other remaining positive root is alpha 1 plus alpha 2. Okay, so these alphas, as I just said, are a basis for the space. So we have dimension many, and the subscript on my root systems will always indicate the dimension of the space we're working in. So it's in fact not so hard to show that the group is generated by just this subset of simple reflections. So my simple roots I'll generally call alpha 1, alpha 2, and so on. And the simple reflections, SI, will be the reflection across the hyperplane perpendicular to the ith simple root.
Christian, there's been a question in the chat. Alex asks, is it equivalent to take minimal elements in the associated poset?
Sorry, I missed the end of the question. You might have muted a little early.
Sorry, is it equivalent to take minimal elements in the associated poset?
Sure. So if we define a poset on the positive roots by, okay, so there is a poset for which the simple roots are the minimal elements. It's called the root poset. I'm not quite sure how to define it. Oh yeah, okay. So we can define a poset. That's a good question. So as a little aside here, we can define a poset. So say alpha is less than beta. So here alpha and beta are both positive roots. If beta minus alpha is still a positive root, then the simple roots will be the minimal elements of this poset, and that's called the root poset. Okay, so that's a good question. Okay, so let's do an example. So I gave you on the last slide a definition of this type AN-1 root system. In that case, the Weyl group is just isomorphic to the symmetric group Sn. So notice the slight difference in indexing here. The reason for the difference in indexing is that I have n-1 simple reflections, and they look like swapping the permutation, which just swaps the ith and I plus first letters. So n-1 of those things generate the symmetric group Sn. So you can see this because I'm in this space where the sum of my coordinates is 0. If I reflect across the hyperplane perpendicular to some root ei minus ej, that's the same as swapping the coordinates in positions I and j of my vector. So all the symmetries generated by these reflections are exactly all permutations of my coordinates. So that's why the Weyl group is isomorphic to the symmetric group. So the other example I showed you, type Bn, in this case, the Weyl group is all signed permutations. So you can think of this as the group of ways to shuffle a deck of cards and flip some of them over. Those sorts of operations, and you compose them in the natural way. So in this case, this is now rank n, because I have still these same simple generators which just swap two cards, but also one which negates the last card. And those together generate my whole group. Now, so Weyl groups are, in particular, they fit into a class of groups called Coxeter groups. Coxeter groups are groups with certain generators which are involutions. So notice that if I take any SI and square it, I get the identity because I've reflected across some hyperplane and then reflected back. And the other relations in this group are encoded by a picture, which is called the Dinka Diagram. So I've drawn those here in orange. And this diagram has one vertex for every simple reflection. And the edges tell us about the relations between them. So if I have no edge between two nodes, that means that those two generators commute. So in the type A example, where my simple generators are adjacent transpositions in the symmetric group, notice if Si and Sj, if I and j differ by more than one, then those will commute. That's why I don't have any edges between generators of non-adjacent index in this graph. This edge here tells me that there's going to be some relation between Si and Sj, and the multiplicity of this edge tells me exactly what it's going to be. So for type A, all of the edges have multiplicity 1. In type B, they all have multiplicity 1 except for this double edge here. So a single edge means that I have this degree 3 relation that, say, Si times Si plus 1 has degree 3, has order 3 in the group. So we can see this in the symmetric group. If I take the transposition I and I plus 1 and multiply that by the transposition I plus 1 and I plus 2, I get a 3 cycle, and that will have order 3. You can check for yourself as an exercise that if I instead look at the product of a transposition like this, swapping m minus 1 and n, and also this extra simple generator, that will have order 4. Okay, any other questions so far? All right, looks good.
And if you have a question, feel free to unmute yourself or ask it in the chat.
Does that like extend? So can the degree be higher than 4? And if so, does like degree 5 mean triple edge and so on?
That's a good question. So if we, right. So if we insist that the Weyl group that we get is finite, which will be the case in my talk today. So the finite Weyl groups coming from finite root systems. Then there's actually a classification of what are all the Dinka diagrams. And there are single edges, there are double edges. There's, I guess, one example where there's a triple edge. And triple edge, strangely, means you have a degree 6 relation. So there is what's called type G2, which has this Dinka diagram. So as a group, it's just isomorphic to a dihedral group because it's got 2 involutive generators and this, so it's like the group of symmetries of a hexagon or 12-gon hexagon. Right. Yeah, so in fact, it's not so hard for me to give you what are the complete list of Weyl groups. So we've already seen the families AN and BN. There's also a family DN whose diagram looks like this. It's got a fork at the end. This is the group, you can realize this as the group of signed permutations, but where I require there to be an even number of negative signs or an even number of cards flipped over. So that's an index 2 subgroup in type B. And then there are a few more what are called exceptional ones. So there are these 3 infinite families of Weyl groups. Then there's also this G2 here. There's something called F4, which looks like this. And then there's a family E6, 7, and 8, which, so for example, E6 looks like this, and E7 and 8 just append extra things on here. Okay, so now you know what all the finite Weyl groups are.
Thank you.
All right. So given a Weyl group, there's something called a parabolic subgroup, which is, it's not just a subgroup as a group, but it's a subgroup which inherits some of this extra structure of these simple generators in this root system that we've been talking about. So capital S is just my set of simple generators, Si, and J is any subset you like of S. Then the parabolic subgroup W sub J is just the subgroup generated by only the simple generators in J. So for example, if we're in type AN-1, and W is the symmetric group, then all the possible parabolic subgroups W sub J are a product of smaller symmetric groups where the sizes of these add up to n. So why is that? Well, if we think about it, what's the effect of, say I take the parabolic subgroup where J is all of S except I've removed one generator Sk. So now I'm allowed any adjacent transpositions except I can't swap K and K plus 1. It's not so hard to see that the effect of that is I never am able to move the numbers 1 up to K outside of the first K positions, or the larger numbers out of the last positions. So this looks like a product of a symmetric group Sk and a symmetric group Sn minus K. And similarly, if you removed more generators, you would get more gaps where you couldn't swap across, and you would get this product of symmetric groups. Okay. Now, sort of dual to the notion of parabolic subgroup is something called the parabolic quotient of the Weyl group. So in order to define this, I'm going to have to define the length function. So the length of an element, so here little w is an element of the Weyl group. It's the fewest number of simple generators I need to write W as a product. Okay, so it's the smallest L can be such that I can write W in this form. So for example, all the simple generators have length 1, a product of 2 simple generators has length 2, unless you've gotten back to the identity. Okay, each coset of this parabolic subgroup in the whole group, so it's not obvious, but I'm telling you it's a fact. That coset, it's just some collection of elements of the group, it has a unique element of minimal length. So whatever the shortest length among all elements of that coset is, there's only one element which has that shortest length. So the set of these minimal length coset representatives is denoted W super J. So that's the parabolic quotient associated to J. So I should say that this, the parabolic subgroup was just that, a subgroup. This a priori doesn't have any nice algebraic structure. It's not closed under products. It's not closed under inverse. It's some nice collection of elements of the group, but it's not exactly an algebraic object itself. Okay, so for each J subset of S, I have both a parabolic subgroup and a parabolic quotient. Now, a proposition, which isn't so hard, it will be interesting to us because we're going to be generalizing this in some sense in the main talk. So if J is any subset of S, the proposition says that every element W in the group can be uniquely written as a product of something in the parabolic quotient times something in the parabolic subgroup. Okay, so just stopping there, that claim is pretty clear. So W sub J is a subgroup, and this, by definition, I've picked out one element in every coset. Okay, so it's just a basic statement from group theory, what I've said so far. What's interesting is that this decomposition is length additive. So the length of the element I started with is the sum of the lengths of these two pieces that I've broken it into. So just as a note, whenever I write W as a product, I definitely have length of W is at most the sum of the lengths. That's because I can take some, so these expressions here of minimal possible length in the simple generators, those are called reduced expressions or reduced words. But in general, I can take a reduced word for this thing and a reduced word for this thing of these lengths and concatenate them, and that will give me an expression which is equal to this thing. So certainly this thing has a reduced word of at most that length, but maybe when I concatenate these, that expression is not actually of minimal length anymore. So it might be that this is a strict inequality. But the claim is that if this decomposition is of this form, if it's the unique one coming from the parabolic quotient and the parabolic subgroup, then I in fact have this length additive statement. Okay, so what does this look like in type AN-1, which remember is the symmetric group? So just for simplicity, let's say J is all of my generators except, oh, that doesn't make sense, except SK. So as we discussed previously, this will mean that the parabolic subgroup is a product of SK and Sn minus K, where Sk is acting on the first K letters and Sn minus K on the next n minus K. The parabolic quotient in this case, okay, so let's think about, so we're supposed to look at, in each coset for Wj, the element of minimal length. So a coset of this parabolic subgroup. So if you think what that means, this subgroup knows how to move the first K positions and last n minus K positions amongst themselves. So in order to specify a general permutation, the extra information that needs to be provided by the coset is which numbers are in the first K positions and which numbers are in the last. So that is, cosets of this parabolic subgroup are in bijection with subsets of size K of 1 up to n, just telling me which numbers are among my first K. Okay, and that makes sense because this group has index and choose K in the full symmetric group. So now remember that the parabolic quotient said that for each of those cosets, I have to pick the permutation of minimal length. So there's a rule for how do I determine the length of a permutation, and it's just the number of inversions. So it's the number of positions of numbers to the left of other numbers, such that the larger number is on the left. Okay, so that's how you can easily compute length for permutations. So if we think about it, so in each coset, we're specified which numbers are among the first K, and I ask you what's the smallest possible length for a permutation satisfying that. Well, I know which numbers I have to have among the first K and among the last n minus K, but in order to avoid extra inversions, I should have these things increasing, these segments increasing. So in other words, Wj are those permutations where the only possible descent is in the kth position. All right. So let's just look at a quick example of that. So if n is 6, so I'm in permutations of 6, K is 3, and W is this permutation I've written here. Its length is 10. We can see that by counting inversions. I've got 1 inversion, 2, 3, 4, 5, 6, 7, so on. There are 10 of them. But we could also decompose this permutation into the piece coming from the parabolic quotient. So notice what I've done here is if you divide after the kth position, I just look which numbers are among the first k and sort those here, and which numbers are among the last 3 and sort them here. The length of this thing we can check is 7. Now the element of the parabolic subgroup is similar, except, well, sorry, it's not similar. The job of this permutation is to say, well, how do I need to sort these in order to get them into the same order as they are in W? And that's encoded by these 2 permutations. And this has length 3. And 7 plus 3 is 10. Okay, so just a little bit of foreshadowing for the talk. So we just talked about if you give me any J subset of my simple generators, I get a parabolic quotient and a parabolic subgroup. The product of these 2 things, if I take all pairwise products, I get a bijection with the whole group because I had everything uniquely decomposing. And that bijection had this length additive property, that the length of the product was the sum of the lengths of the parts. So in general, if I have any subsets X and Y such that the multiplication map from X cross Y to W is a length additive bijection. So for example, take this to be a parabolic quotient and this to be a parabolic subgroup, we'll call that a splitting. And in the main talk, I'm going to be talking about more examples of splittings of Weyl groups. And so that's what I've got for the pre-seminar, and I'm happy to answer any questions.
Remember, if you have a question, you can post in the chat or unmute yourself.
Where does the term parabolic come from?
So I can give a partial answer to that, and that I can reduce it to another instance where parabolic appears, and I don't know where that comes from. So Weyl groups, the reason Weyl groups are studied is because of Lie theory. So a lot of the structure and representation theory of Lie groups is determined by their associated Weyl groups. So for example, roughly speaking, the Lie group SLN corresponds to, has Weyl group symmetric group SN. And if I look at the subgroup inside here, where I only allow matrices which have this sort of block upper diagonal form, but are zeroed on here, this is a parabolic subgroup of the full Lie group, and its Weyl group is a parabolic subgroup of the Weyl group of the Lie group itself. I'm not entirely sure why these are called parabolic, but
I'm also not familiar with the Weyl group of a Lie group, but
sure,
so,
okay.
but I assume that there's a lot of background there that I would need. I'm not familiar with Lie theory at all, so.
At least you have a few words now that you can Google if you're interested.
Okay, well, if there are no more questions, let's thank Christian. So applause doesn't work so well over Zoom. You should have a button for reactions, and then there's a hand clappy thing, or post in the chat.